Welcome. Today we're diving into the fascinating world of sound propagation. Have you ever wondered how you can hear someone calling your name from across the room, or how music travels from speakers to your ears? It's all thanks to the way sound moves through different materials. In this video we'll explore what sound is, how it travels, and what factors affect its journey. By the end, you'll have a clear understanding of the science behind everyday sounds. Let's start by understanding what sound actually is, and why it needs a medium to travel. Sound is a type of energy that we perceive with our ears. It's created when something vibrates, causing the surrounding air, water, or solid materials to vibrate as well. These vibrations travel as waves, carrying energy from one place to another. Unlike light, sound cannot travel through a vacuum because it needs a medium like air, water, or solids to move. This is why you can't hear anything in outer space. Understanding this basic concept is key to grasping how sound propagates. An object vibrates, it pushes and pulls on the particles around it. These particles bump into their neighbors, passing the vibration along. This chain reaction creates a wave that moves outward from the source. Think of a drum. When you hit it, the drumhead vibrates, pushing air particles and creating sound waves that travel to your ears. This process happens incredibly fast, allowing us to hear sounds almost instantly after they are made. Sound waves are a special type of wave called longitudinal waves. In these waves, particles of the medium move back and forth in the same direction as the wave travels. This is different from water waves, where particles move up and down. In a sound wave, areas where particles are close together are called compressions, and areas where they are spread out are called rarefactions. This pattern repeats as the wave moves through the medium. Sound needs something to travel through, called a medium. The most common medium is air, but sound can also move through liquids like water and solids like metal or wood. In fact, sound often travels faster and farther in solids than in air because the particles are packed more closely together. That's why you might hear a train coming by putting your ear to the track before you hear it in the air. Speed at which sound travels depends on the medium. In dry air at room temperature, sound moves at about 343 meters per second. In water, it's even faster, around 1,480 meters per second. And in solids like steel, sound can travel at over 5,000 meters per second. The closer and more tightly packed the particles, the quicker the sound can move through them. Space is a vacuum, which means it has no air or other particles. Since sound needs a medium to travel, it can't move through the emptiness of space. That's why astronauts use radios to communicate. They rely on electromagnetic waves, not sound waves, to send messages. Our ears are amazing tools for detecting sound. When sound waves reach your ear, they cause your eardrum to vibrate. These vibrations are passed through tiny bones and turned into signals that your brain can understand. That's how you recognize voices, music, and all the sounds around you. The amplitude of a sound wave determines how loud it is. Amplitude is the height of the wave. Higher amplitude means a louder sound. When you shout, you create sound waves with greater amplitude than when you whisper. Our ears can detect a wide range of amplitudes, from the faintest rustle to a roaring jet engine. Frequency is another important property of sound waves. It's the number of waves that pass a point each second, measured in Hertz Hz. High-frequency waves sound like high-pitched notes, while low-frequency waves sound deeper. That's why a piccolo sounds much higher than a tuba. Our ears are sensitive to a wide range of frequencies, which lets us enjoy all kinds of music and sounds. Wavelength is the distance between two consecutive compressions or rarefactions in a sound wave. It's closely related to frequency. Higher frequency means shorter wavelength, and vice versa. Wavelength helps determine the pitch and how sound interacts with objects in its path. Sound waves can bounce off surfaces just like light. This is called reflection. When you shout in a canyon and hear your voice echo back, that's sound reflecting off the canyon walls. Reflection is used in sonar and in designing concert halls to enhance acoustics. Not all sound waves bounce back. Some are absorbed by materials like curtains, carpets, or foam. Absorption reduces echoes and makes rooms quieter. That's why recording studios use special panels to absorb sound and prevent unwanted noise. When sound waves pass through a material, that's called transmission. Some materials like glass or metal let sound pass through easily, while others block it. The thickness and density of the material affect how much sound gets through. This is important in building design and noise control. Sound waves can bend around obstacles and spread out after passing through openings. This is called diffraction. That's why you can hear someone talking even if they're around a corner. Diffraction allows sound to reach places that light cannot. When two sound waves meet, they can combine in interesting ways. If their crests and troughs line up, they create a louder sound. This is constructive interference. If they're out of sync, they can cancel each other out, making the sound quieter or even silent. This is called destructive interference. Resonance happens when an object vibrates at its natural frequency due to sound waves. This can make the sound much louder, like when a singer hits the right note and a glass vibrates. Resonance is used in musical instruments to amplify sound. Echoes are distinct repetitions of sound caused by reflection from distant surfaces. Reverberation, on the other hand, is a series of overlapping echoes that blend together, making the sound last longer. Both effects are important in designing auditoriums and theaters. The Doppler effect occurs when a sound source moves relative to an observer. As the source approaches, the sound waves are compressed, making the pitch higher. As it moves away, the waves stretch out, lowering the pitch. This is why an ambulance siren sounds different as it passes by. Air is the most common medium for sound on Earth. The molecules in air are spaced out compared to solids and liquids, so sound travels slower here. Everyday sounds like talking, music, and traffic mostly move through air to reach our ears. Sound travels faster in water than in air because water molecules are closer together. This is why whales and dolphins rely on sound to communicate over long distances in the ocean. Submarines also use sonar to detect objects underwater. In solids, particles are packed tightly, allowing sound to travel even faster. That's why you can hear a train coming by placing your ear on the track. Engineers use this property to detect faults in materials using ultrasonic waves. Temperature affects the speed of sound. In warmer air, molecules move faster and transmit sound more quickly. That's why sound travels faster on a hot day than on a cold one. This effect is important in weather forecasting and outdoor events. Humidity also influences sound propagation. Moist air contains more water vapor, which makes it less dense than dry air. Surprisingly, sound travels slightly faster in humid air. This is why you might notice differences in how sound carries on a rainy day. Sound barriers are structures designed to block or reduce noise. Highways often have walls to protect nearby neighborhoods from traffic noise. These barriers absorb, reflect, or deflect sound waves, making environments quieter and more comfortable. Ultrasound refers to sound waves with frequencies higher than humans can hear. These waves are used in medical imaging, like checking on babies before they're born. Ultrasound is also used in cleaning delicate objects and detecting flaws in materials. Infrasound is the opposite of ultrasound. These are sound waves with frequencies lower than humans can hear. Some animals, like elephants, use infrasound to communicate over long distances. Scientists also use infrasound to monitor natural events like earthquakes and volcanic eruptions. Sound propagation has many practical uses. From medical imaging and underwater navigation to noise control and entertainment, understanding how sound travels helps us design better technology and environments. Engineers and scientists rely on these principles every day. Musical instruments create sound by vibrating strings, air columns, or surfaces. The shape and material of the instrument affect how sound waves are produced and amplified. That's why a violin sounds different from a drum or a flute. Our voices are produced when air from our lungs vibrates our vocal cords. The sound is shaped by our mouth, tongue, and lips to create speech. Each person's voice is unique because of differences in their vocal tract and how they use it. Animals use sound to communicate in many ways. Birds sing to attract mates, dolphins whistle to coordinate hunting, and elephants rumble to signal danger. Each species has adapted its sound signals to its environment and needs. Hearing loss can occur when parts of the ear are damaged or blocked. Loud noises, aging, or infections can all affect our ability to hear. Understanding sound propagation helps doctors diagnose and treat hearing problems more effectively. Noise pollution is unwanted or harmful sound in the environment. It can come from traffic, factories, or loud music. Prolonged exposure to noise pollution can affect health and well-being, making it important to control and reduce noise in our surroundings. Architects use knowledge of sound propagation to design buildings with good acoustics. The shape, size, and materials of a room affect how sound travels and is heard. This is especially important in concert halls, theaters, and classrooms. Sonar stands for sound navigation and ranging. It uses sound waves to detect objects underwater. Ships and submarines send out sound pulses and listen for echoes to map the ocean floor or find obstacles. Sonar is crucial for navigation and exploration. Seismic waves are a type of sound wave that travels through the Earth during earthquakes. Scientists study these waves to learn about the Earth's interior and to predict natural disasters. Seismic waves can be both longitudinal and transverse. Hearing aids are devices that amplify sound for people with hearing loss. They use microphones to pick up sound, process it electronically, and deliver it to the ear. Advances in technology have made hearing aids smaller and more effective. Noise-canceling headphones use special technology to reduce unwanted sounds. They detect incoming noise and produce sound waves that cancel it out. This makes listening to music or calls much clearer, especially in noisy environments like airplanes. Bats use echolocation to navigate and find food in the dark. They emit high-frequency sounds and listen for the echoes that bounce back from objects. This helps them see with sound, even when there's no light. Underwater, sound is the main way to communicate because light doesn't travel far. Submarines, whales, and dolphins all use sound waves to send messages and detect objects. Special equipment helps humans communicate and explore beneath the waves. Scientists use sound waves, specifically seismic waves, to detect earthquakes early. Sensors pick up vibrations in the ground and send alerts before the shaking reaches populated areas. This technology can save lives by giving people time to prepare. Soundproofing is the process of making a space resistant to sound. Special materials and construction techniques are used to block or absorb sound waves, creating quieter rooms. This is important in recording studios, offices, and homes near busy streets. Protecting your ears from loud sounds is important. Earplugs and earmuffs help reduce the amount of sound that reaches your eardrums, preventing damage. This is especially important for people working in noisy environments like construction sites or concerts. The study of sound propagation continues to inspire new technologies. From advanced hearing aids and smart speakers to improved noise control and medical diagnostics, understanding sound helps us innovate. The future holds exciting possibilities for how we use and control sound. We've explored the journey of sound from its creation to how it travels and is used in our daily lives. Sound propagation is a fundamental part of science, technology, and communication. By understanding how sound moves, we can better appreciate the world around us and develop new ways to harness its power. Thanks for joining this exploration of sound propagation.